Okay, thank you for the introduction, and thank you again for the invitation and for all of you being here. So the main construction I'll go to talk about towards the end of the talk today is joint work with Jeff Brock, but I'll mention here collaboration with a few people around here in the room. But let me tell you a little bit the story, especially because since this talk is maybe a little bit less based on what is happening in the probability side, but it's maybe more trying to present and advertise some geometric construction that had appeared, as product of all these interactions we're having between probability and geometry. Okay, so I'm going to start setting up some notation and elements that have appeared in some way, shape, or form. So just maybe for simple notation, this is going to be just my standard presentation for the Riemann sphere. The usual unit disk, its complement, and the unit circle. I will be referring to the group of Mobius transformations as PSL2C. Right, so these are going to be all the linear maps of the following form, CC plus D, here under the condition that the determinant is equal to 1. And I really want to think about it as a linear transformation, not just as the matrix. So multiplying by -1 does not change what my map is going to be. Okay. So in the previous talks this morning, we saw already introduce a Teichmüller space, but I want to introduce maybe a bit of a bigger space known as a universal Teichmüller space. And I'll present it for you to have something concrete to hang on, although I'm not going to be using very formally a lot of the features, but let me introduce this in a few different ways. So maybe for the starters, one, and should tell you, this is going to be my notation for it. So I'm going to start defining it as the following. I can look at quasi-symmetric isomorphisms of the circle to itself. So these are just homomorphisms from the circle to the circle, where if I take 3 equally spaced points, well, after I apply my homomorphism, they are not going to be equally spaced in general, but the ratio how much I'm stretching and contracting some parts in something that is going to be controlled by a given constant that depends on my quasi-symmetric map. So I'm going to have this. I'm going to quotient here, well, not by the whole PSL2C, because this does not preserve the circle, but just looking at the Mobius transformations, preserving the circle as a set. And you could see this by a one-to-one correspondent as just quasi-symmetric maps such that they fix. I'm allowed to fix up to 3 points. So let's say I fix ±1 and -I. Okay. So right now this is just introduced as a set. Maybe if I want a new introduction, a little bit more structure, I can look at the following. So I'm going to look at the unit ball of the Beltrami differentials in the complement of the unit disk. So that these are just going to be L-infinity functions in here, such that their L-infinity norm is controlled by 1. Okay. Now, something that you could do here is just by taking reflection with respect to the circle, I can extend in a very natural way this mu. So now it's going to be defined as a Beltrami differential over the whole Riemann sphere. And I can look to W mu, mu down, as the homeomorphism that solves the Beltrami equation for this extension. So the Beltrami equation is going to be d bar mu equals mu time derivative of this. Okay, so it's not a conformal map. It's going to be a quasi-conformal map where the quasi-conformality is going to be given here by the extension given by mu. Now, because we consider, and again, so that this map is well defined, a lot of these things I will keep saying they fix ±1 and -I. So now because of this has been given as the extension, then it turns out it's not hard to see, given the solution, the understanding of the solutions of the Beltrami equation, that this has to send the circle to the circle, rescuing the quasi-symmetric description I was giving you here before. But then moreover, this defines an equivalence relation between two Beltrami differentials as they're going to be equivalent if and only if this extension to the circles happen to agree. And then you could see universal technical space as just quotient this by this equivalence relation. Okay, so that's version number 2, and I'll come back a little bit later to tell you one more bit of information there. But now something else you could do here is, here I extended mu towards the unit disk by using the reflection along the circle. I can just extend it as a 0 map. When I do that, I will get now the solution now gets to be conformal on the disk. So then I can say extend as 0 into the unit disk to now get a map. So I'm going to have it here as an upper script. So this is going to be, again, from the Riemann sphere to the Riemann sphere, solving the same equation for this. And which in particular defines a map that's going to take any equivalent class of Beltrami coefficient in here to, well, a conformal map by restricting this map, this solution towards this. Right, so now this gets to be an holomorphic map from the unit disk into some domain of the Riemann sphere that has some quasi-conformal extension to the complement. And that's exactly what this is identifying T1 with. So here I'm going to have holomorphic maps such that F extends as a quasi-conformal map. And again, the clause of fixing plus minus 1 minus I. Again, this is just because you need essentially 3 points to determine a Mobius transformation. Okay? So now under this, what I could look at here is, given that I have this image, we could look at the following. We could look at the image of S1. So now this is going to be a Jordan curve in the Riemann sphere, which passes through, again, plus minus 1 and minus I. But again, it's not any given Jordan curve because I'm assuming it's living within all this extension that has to be quasi-conformal in the whole space, which is usually what we call as a quasi-circle. Okay. So let me remember to avoid maybe this part so it's visible to the crowd. Okay. So this is with respect, is 3 different ways. Again, I'm aware that maybe people in the audience are maybe very familiar with this, but I just wanted to have something on the board so we're on the same page. So then I just want to clarify, during the previous talks, the Bell-Peterson metrics, so maybe 2 things I should say, is that here really, by universal Miller space, I mean the Teichmuller space of quasi-circles in the Riemann sphere, which is a little bit more general than the Teichmuller spaces we were seeing in the morning. The realization you can see is that those Teichmuller spaces, let's say through the double uniformization theorem, you can realize them as quasi-circle belonging to this class. So in particular, this space is going to contain copies of all the Teichmuller spaces we saw in the morning. So observation 1, observation 2, in the talks in the morning, this Bell-Peterson metric was discussed. It was a very natural metric to have there. It was used to talk about probability in the space of surfaces. That metric has a natural extension to this space, which is the, again, the Bell-Peterson metric for T1. Now, here the distinction, as you said, has as follows, is that as I'm presenting here, this is not going to be any more a finite dimensional space. So it's going to be infinite dimensional, so I have to be a little bit more precise in what do I mean by this particular metric. So let me clarify, maybe say a couple of things about the structure of this, is that from definition 2, you can see there is a natural projection that goes from these Beltrami coefficients to T1. This is just, I take my Beltrami coefficient, I consider its associated class. This is naturally a complex manifold. Right? These are just, it's clear what the notion is here. But it turns out there exists canonical complex structure in T1 that makes this an holomorphic submersion. Okay. So now, under this identification, what is going to be important, at least for, so I won't give you the whole discussion, the whole metric, but I want to give you at least a discussion of how the metric looks at a very particular point. So for this, what I could look here is, well, maybe I should have say to you as an example that over here I have the identity map, I have the class of the Beltrami coefficient that vanishes everywhere, and I have the usual round circle as a quasi-circle. Okay, so all of these are the same entity navigated through all these equivalences. So I will give you the tangent space at that point, and the tangent space at the round circle, well, this is going to be identified as the quotient of this map, well, by the kernel of the derivative of the map at 0. And these are going to correspond to, so maybe I won't bore you. Sorry, maybe I can just put it quickly here as harmonic quadratic differentials. So these are just going to be a particular so I'm going to have here coefficients so that this is going to be given as follows. So sorry, I have to tell you a little bit what this all means. Sorry, I have to go all the way over the board. Okay, so in there, by this factor, by rho d star, I mean this the Poincare metric in the bar. Namely, there is this model for what the hyperbolic metric in the plane is, and this is just going to be a symbol for the metric, or rather for its conformal factor. And their phi is just going to be given as follows. This is just going to be a map from here to the disk, which I'm going to assume holomorphic, so that the following supremum is going to be bounded. So I'm going to have here so this has to be bounded when I consider here all points of the disk. Okay. So I have that particular class of particular way of identifying what the tangent space at that point is going to be. I should say, oh, sorry, I'm erasing this, but there are a lot of canonical structures, a lot of canonical group structures here. For instance, from the viewpoint of quasi-symmetric maps, it's handy because you can compose those maps of the circle to get another quasi-symmetric map of the circle. So you could use that to basically propagate a lot of the structure I'm telling you at one particular point throughout the whole setup. But well, then just for you to define for you what the Bell-Peterson metric is going to be. So I'm going to take two harmonic differentials. I'm going to define their inner product as follows, and I have to be here, give you a bit of information. So I'm going to try to take their normal inner product weighted here by the Poincare metric. Now, the point here is that because we're not dealing anymore with compact surfaces, so if I had a compact surface before, then I could just say this to you, hey, this is another way for you to see developing isometric you saw last time in the morning. The issue here is because my domain is now being identified with the full complex, with the full hyperbolic plane, having this being as an element that is going to be bounded is not enough for me to know that I will be able to integrate this. Okay? So now, not for any pair of harmonic differentials I'm going to have, this integral is going to be well defined. I will have to restrict myself to the harmonic differentials here that are going to be squared integrable for me to be able to take that procedure. So then really what this is going to do, long story short, is going to create at every point in universal 10-meter space a distribution of directions where this inner product happens to be finite, meaning when you're looking at directions that are going to be L2 integrable. And then I will quickly denote it here, T01, known as the universal universal Bell-Peterson space. This is going to be the component of integrating the distribution through the origin. Okay. Okay. Oh, sorry. Right. Okay. Okay. So from here, again, maybe I think a lot of you are certainly way more qualified than me that complete the following. But basically, this is an interesting setup when one is thinking about, let's say, either setup one is trying to look at either random curves or random paths in the plane. Now, there is one more bit of information on the theoretical side that I would like to tell you, which is quickly mention something about universal Liouville action. So for that, I will point out the following. And again, I should tell you, for a lot of it, I will think about this space, either universal 3-meter space, or in particular universal Bell-Peterson space, as just the class of a quasi-circle living in the Riemann sphere up to some Mobius transformation. Namely, when a Mobius transformation acts, I'm still thinking about it as the same object as described through all these equivalents. So once I have this, then for each component through uniformization, I have a uniformization map here defined from the disk, for the complement of the disk, and the associated universal Liouville action for this curve defined as the following. You integrate this over the disk, you integrate this function of g over the complement of the disk, then you have this normalization factor 4 pi log derivative of f at 0, derivative of g at infinity. Again, there are some assumptions here I'm throwing under the rug. I think I have to assume that my curve here is going to be bounded for this to make sense in the way I'm saying it. And that infinity is where g is being mapped, but let me not worry too much, other than to say that through this functional, one can see a characterization of being in this particular component of integrating as follows, that a particular quasi-circle is going to be WP, meaning belonging to T10, if and only if this quantity is a finite quantity. Okay, again, that's not.
What you call this quantity is the Loewner energy, right?
Sorry. Yes, sir. I didn't grade it. I said it. Is sorry. What should be the proper name?
Loewner
Yes. So I was gonna say this is equal, and again, here I'm getting everything up to a constant. So I'll try to find the constant. I think the constant is pi. It may not be pi. If it's not, feel free to correct me. This is equal to pi times the Loewner energy associated to the curve. Yes. Okay. But this helps me with the following point, which is that if someone presents you this and tells you, hey, by the way, this is invariant up to the Mobius formations we're acting, this is not a very obvious theorem to prove, especially if you're just presented to this. This is the first time you see this description. This is something rather surprising. And one way, I guess, one way to have the proof is to prove this, and then from here, that invariance is a little bit more natural. Okay, so that's one setup. I'll come back to that moment, but let me tell you maybe two more important properties. One is that this is always going to be non-negative, and moreover, you have equality if and only if gamma is going to be a circle. And then moreover, this is not just any functional. This is a Kähler potential for the Bell-Peterson metric. Namely, remember, there is this canonical composite structure I was telling you this is basis half. And if I take delta delta bar of this, again, up to the appropriate constant that I think I shouldn't put anything here, but again, if I'm missing a constant, please let me know. You will recapture here the Bell-Peterson metric I gave you. Okay. Okay, questions up until now? Cool. Okay, so this is just presenting a lot of elements. A lot of them you may be already familiar with. The part I want to anchor, or the part of the discussion where this interaction has been happening is precisely in the comment that a lot of these constructions, namely the objects themselves, either in universal Tengmuller space or universal Bell-Peterson space of this functional, they are PSL2C invariant. PSL2C, this group of linear complex transformations, they extend naturally as the isometries of H3, namely you have your Riemann sphere. The Riemann sphere is the conformal boundary of hyperbolic space H3 living inside. There are all the extensions of all the isometries, but I didn't need it to say any hyperbolic geometry in order for me to complete all these sentences up until here. So it's almost as, in a way, the theory is not using hyperbolic geometry, but a lot of the language is being poised for you to think, wait, there should be some geometry attached to a lot of this function or to a lot of these concepts on the hyperbolic side. That link should exist even just by the PSL2 invariance, even though you get to say all these beautiful sentences without appealing to the power of hyperbolic geometry, which is the field where I come from. Okay, so that has been a lot of the points of a lot of like recent interactions. So let me I'll quickly say two results, and maybe I will be a little bit more precise a little bit later. So one is joint work with Bridgman, Bromberg, myself, and Eileen present here, which I will announce it right now as this action can be expressed as a volume functional in H3. And let me mention maybe the other one, which helps me tie with this. So this is with Eileen, also present here, and with Catherine, that I think I saw there at the back, which is, I was focusing here a lot more with this functional that is defined in the quasi-circle sense. If I was thinking about from the size of quasi-symmetric map, there is a somehow similar, I feel like maybe there may or may not be a more discussion of this later in the week. But there is another functional known as the Schwarzschild action, So I will write it here as the Schwarzschild action, which is now it's a functional defined, again, at the level of quasi-symmetric map of the circle, can be expressed, and I will just say here, as a length / area functional. And then, again, I won't go much in detail other than saying that the only, again, I don't know if any of you has a particular opinion. I will just say there is a funny identity here that identifies a length with an area. So that's why you see me being a little bit indecisive if I'm calling this rather a length versus an area. I will say here this happens in H2, in the hyperbolic plane. Okay, so we have seen some realizations. We have seen some realizations of this factor. Okay, but that's a little bit the story that I want to tell you. Especially, a lot of people in the crowd have all these ideas about like how these spaces appear for problems in probability, for you to see a little bit where the construction in geometry is coming from. And what are some of the other things we're doing with it? Just hopefully something you see. And this talk made like, if you have any comments or any ideas, please let us know. But okay, now I just want to start very loosely trying to explain how this idea, how does one do this construction, without trying to overwhelm you, but just keep throwing formulas at your face. I'll try to be vague, but I still try to tell you something. As I was saying before, here is my ball model of H3. Okay. The metric, well, if you're curious what the metric looks like, it's just going to be given by this. And here I just have the standard Euclidean metric. So it's infinitely large. It's very symmetric, constant curvature -1. And the Riemann sphere appears as the boundary at infinity, namely, it's only the interior of the space what belongs to hyperbolic space. The boundary of the sphere is infinitely large. It's infinitely far from any point. Now, what I would like to have is I would like to have a parallel that allows me to either take information from the conformal boundary and make a geometric picture in the interior, or vice versa, having a particular geometric picture in the interior and allow me to recapture that some conformal information at the boundary. Okay, that's sort of like the ping pong we're interested in playing. So one way to do that is the following. So I'm going to declare here my origin. I'm going to have here a point x. I'm going to consider the following. So I'm going to take rho x. This is going to be any isometry of hyperbolic space that takes x into the origin. Okay, this is a very symmetric space. If you have not seen it before, it's not hard to find even like a precise formula for what this looks like. But take any of them. And now you're going to take the pullback of the round metric of the boundary. Okay? And this is known as the visual metric from X for the conformal boundary. It's going to be conformal to the previous metric of the sphere, because again, I told you this is given by some fractional linear transformation by a Mobius map. So this is just this map is just going to be conformal. It's just going to change the metric, the original standard metric for the sphere, by some other metric that also has constant curvature 1. And the reason why it looks what is said to be the visual metric is because of the following. Another way to defining it is to do the following. I can take all the unit vectors departing from X, and I just shoot all of them towards infinity at the same speed. Every one of these points is going to hit some point in my boundary sphere. Now, the space of unit vectors with base point at X, that's a sphere with curvature 1. It's a sphere with the maximal ranges of symmetry. And now when you flow by this geodesic flow and show it to infinity, well, you could just push the metric along and this is how x is seeing infinity. So you could imagine this metric is if you are just an observer standing at x, if you start measuring distances according to how your normal vector varies. So it's a very natural geometric construction to consider. Now, the interesting part here will be the following. So let me, maybe I'll just redo here so my picture doesn't get too busy. Let's say I have a point here, and I have already decided what my conformal metric is going to be. I've already decided here V at the point P. This is a conformal metric at P in S2. So I just fix a conformal factor with respect to the wrong metric if you wish. And now I wonder what is the set of points that will see this point at infinity exactly with that metric. So it turns out, this is a little nice geometric exercise, that that whole set, the solution set, is what we call as an orosphere. So it's going to be a little sphere that's going to be tangent to that precise point at infinity, and the size of that orosphere has to do with how big or how small was my conformal factor. Okay, it's not too hard. Again, I won't bother much with the exercise other than saying that when you start looking at how the visual metric factor changes when I move the point, the kernel of that map happens to be all the planes tangent to this orosphere. So of course, the solution of having my functional being constant is an envelope that is tangent to all those planes. So now, so I have this. So from one side, going from the inside to the outside is the visual metrics. From the outside, from the conformal boundary, if I have a given conformal factor, then that's not going to determine to me a point because there are going to be multiple solutions, but it's going to restrict it to a precise family. Now, on this, let's suppose I have in my Riemann sphere, which I'm identifying here with the round 2 sphere. I just have some domain with a conformal metric, which I'm going to denote here by rho. Then we'll define what is known as an Epstein map associated to rho. This is going to be a map from my region to the set of unit tangent vectors here in H3, just as follows. So here, I need one more color. So this is my domain omega. Each point in omega gets to have a vote for what size my orosphere is, right? Maybe here my conformal factor is very big, so I have that. Maybe over here my conformal factor is very small, so I have like a very small orosphere. Okay, but I'm assuming my metric is varying in a sufficiently regular way, so my orospheres are like a nicely behaved set. So now what I could do is I could consider the envelope of all these orospheres. Or if you want, if you imagine my hyperbolic space is made out of ice cream, right? I'm just scooping the interior of every oroball as I go. I'm going to be left with some particular region here. And what my Epstein map is going to determine, so I'm going to have a family of orospheres, and I have a tangent, I have more than the point. I also have the vector, because given that I am a point standing on my orosphere, I know what my normal should be pointing out. So I gather all the information. Again, this was something that was studied by Epstein in the 80s. There is a very precise formula what that is. This depends on the one jet of your metric. Again, I won't write it because it won't mean much for us, other than me telling you, hey, there is a very precise map that takes conformal metrics in here, and it gives me Gauss maps of surfaces. So it gives me a data of not only a surface, but a choice for their normals. Now, of course, the unit tangent vectors of H3 has its projection map to H3, and this composition is what a lot of times we may call an Epstein surface associated to the metric. Now, a couple clarifications about this construction. So I'm calling this a surface, even though a lot of times it may degenerate For instance, if I give you the visual metric of a point, your answer is just going to mean you're just going to give me back that single point, right? So the whole figure is going to collapse to one point. But even though you have those degeneration, and this is not a proper surface by itself, the fact that you have a choice of a normal tells you that, OK, most things you were going to try to do using differential geometry, most of them are going to work, right? You may need to have a little bit, you may need to be a little bit tricky with some computation, but for all purposes, you can imagine them as a nice surface. What I should say? This construction is geometric in the following sense, meaning in the sense that if I take a Mobius transformation A and I pull back a metric by a Mobius transformation, then I could find the solution, or I could find the solution when I take the pullback, and this works for any map for any isometry in PSL2C. So now, with this, again, in a nutshell, all of this is creating is that whenever you have a theory of surfaces here in H3, you have sort of like a mirroring theory of a conformal metrics in certain regions at infinity. So you could always try to use this to either bring or push problems from one side to the other one. Now, how is all of this interplaying with this particular story? Again, without me having to give you every possible detail of the construction, is because of the following. So again, I'm going to have here the unit disk. I have over here my quasi-circle gamma and a region omega. So here is my uniformization map F with here inverse F inverse. So now there is a very natural way to put the hyperbolic metric in here, which is, well, I have a hyperbolic metric in the disk by using the disk model, and I have a conformal map. So I just push it by the conformal map. So that's going to be what the Poincare metric is, and can just be defined as the pullback by F inverse of the Poincare metric of the disk. Now, when you do this, now you have here a nice conformal metric in a domain. So I could look to what this Epstein map is drawing me. This Epstein map is going to draw a surface in the interior for me. The interesting property and what makes, not the only thing, but a lot of it, what it makes jumpstarts this discussion is that for the Epstein surface, you have your principal curvatures, meaning at every point you have the direction for which your surface is trying to curve the most, and the direction for which your surface is trying to curve the least. It turns out that those directions are given in terms of the norm of the Schwarzschild of the inverse of your uniformization. So it's a very nice, a simple formula for this. So how much my surface is going to be curving is given by how much this. Again, didn't say much about the Schwarzschild. Maybe I will just quickly say that, given that I have any conformal map, at any point, you have a best fit by a Mobius map by just approximating that particular conformal transformation by a Mobius map up to, if I'm not mistaken, is the 2-jet. And then when you derivate that, that's exactly what the Schwarzschild derivative is. It's your error from being a Mobius map locally. And and one reason for that is the following. From that, you could deduce the following corollary, which is for your Epstein surface, you could look at what the mean curvature is. So this is the average of your highest and smallest curvature. This is just the area form associated to your Epstein surface. This is going to be equal to the following expression that just follows from that identity I gave you that I'm copying here so I don't mess it up. This is going to be the area 4 of the Poincare metric. And now, the integrability of this expression was tied to the fact that if my curve was Veil-Peterson or not. But if this integrand is the same as that integrand, well, I can just now test if my curve is in WP or not by just integrating the mean curvature of the associated Epstein surface. So then, in particular, my curve is WP if and only if the integral over, this is the Epstein surface associated to the Poincare metric, if its mean curvature is integrable. Okay. Okay. So this is good. So now we can see at least, and it's not the only realization you have with, sorry, how much time do you have? 5 minutes? Okay. I'll start like wrapping it up. So it's not the only characterization where you can get hyperbolic space in both, but the one that is important here is going to be the following. It's going to be like, I can look at the following type of functional. So I can look to the volume by the region in the interior of the Epstein surface minus a half this mean curvature integral over here. And this is the volume functional I was telling you that this is known as renormalized volume. And again, I won't go much in detail other than that waving my arms and telling you this is the right functional to derivate in order to match what the Liouville action is going to be. In particular, or maybe why a function like this will work, just quickly tell you, remember that the derivative of volume is given in terms of the area form. The derivative for area is given in terms of mean curvature. So there is some nice cancellation here to match what the variational formula, to have a nice variational formula. And the fact that the curvature that governs this surface, they're giving in terms of the torsion, which is what was appearing at the other side. Okay, that's usually the punchline. In the cases when and when I say we, I mean the hyperbolic people coming from hyperbolic geometry, is that usually this is given whenever you have a co-compact action. That's just because compact things make our life easier. In this case, particularly in this one, we're not working anymore in a compact domain. So a lot more care has to do with showing all these expressions have to converge. Okay. So that's for now for all of that. And I think, maybe now can erase my title and this. So So for this construction, or the construction I'm telling you here, we're using a very precise conformal metric, right? Us pushing the Poincare metric of the domain. Now, there are a lot more options we could use for conformal metrics on a domain. And a lot of them happen to be involved with functionals you all will maybe interested. In particular, if I look, I'm just going to call it W volume, but it's just a volume functional defined very much in this way. There is a way to define a volume functional associated to a metric in my domain and a conformal rescaling, so that the following identity is going to happen. This is going to be 3 times pi log determinant of the Laplacian of this metric minus log determinant of the Laplacian of this metric. Okay? So this is measuring that how this volume, namely the expression volume enclosed minus half bending of the boundary, is changing if I'm not changing the conformal type of my curve or my domain. If I'm just changing the conformal metric just by some rescaling, is the same as how the logarithm of the determinant of the Laplacian is going to change. Okay, and this was something that was already noted for the co-compact case, but by previous authors. So then here, let me just tell you, theorem with Brock Vargas Pallete is that this identity holds for metrics in domains omega, where the boundary of omega is the union of finitely many circles. And so for that, so let me give you, okay, I know, sorry, I'm getting out of time, so let me give you maybe here, yeah, sorry, I wrote the statement, but then I have to immediately cover because this is where my picture ended. Let me try to explain you a little bit what's happening in this picture. So over here, this is my domain omega. That here I'm just representing on the plane. The only condition is that every boundary has to be a round circle. Here in yellow, so I'm seeing here, I guess, without telling you, I switched to a model of hyperbolic space, which is the model of the half space. So this is going to be my model. But anyway, but every circle is the boundary of one total geodesic plane, which here is representing in yellow. And now I'm assuming that here in omega, I just have some conformal metric. I know, well, this conformal metric is going to draw for me in hyperbolic space a piece of a surface here drawing orange. And I already know from the experience that we have in the compact case, hey, if I was able to derivate whatever is the volume enclosed by this region in orange minus half the bending, I will have a functional that captures the conformal change of log determinant of the Laplacian up to some 3 pi 5. So that's the lesson we have. Now the issue is like here you can see this orange region is not bounding a volume for me to say like, hey, here is the volume you are considering. So what we do is the following, and what the picture does is a lot simpler than the computations, is that well, the metric is defined up until the boundary. At every boundary point, I could redo the envelope problem, meaning the region in orange was found by I draw all the order spheres, I scoop all the ice cream, and this was what it was left at the top. But now I could do the same by only considering the metric at the boundary. So now I'm going to be erasing order spheres, but only going along each boundary component. Now the solution is not just going to be anymore just one single point. It's going to be a whole arc that is going to pass through the solution that the 2D problem had, all the way from where my base point is. And I'm going to have one of these circular arcs per every point to infinity. So now what you could do is you could travel through that circular arc to land in this total geodesic plane. Because once you do that, then you can just use that plane to cap off your region. And now I have, I need to cap off my region for the big plane, and I need to cap it twice, each for these smaller planes here in the picture. So now this finally defines a nicely enclosed picture for which I can say, hey, compute the volume on that. It has some weird piecewise boundary, but I can still say, hey, compute half the bending on that. And that's the W volume. That's the W volume that satisfies this identity. So, okay, so sorry. I know I'm already out of time, so let me stop there. Thank you.